All right, we are starting chapter 18 in Strength of Materials, and this chapter is about columns. Now, we have just finished looking at beams, and a beam is basically any horizontal member that has loads applied to it. Typically, the loads are applied perpendicular to the beam, not always, but mostly. And the most common type of beam support we looked at was a simply supported beam, which had a pin, which provides two reaction forces, and a roller, which provides one reaction force. So there are three reaction forces. A column is basically just a beam turned up on its end, in the sense that it's a structural member that is oriented vertically, and it too has support conditions at either end. The most common of which is not pin roller, but pin. So we have two supports at the top and the bottom that resist vertical and lateral loads, but allow rotation to occur about the base. We are not going to be looking at any lateral loads on our columns. That type of structural analysis gets a little too complicated, so we are only going to be looking at axial compressive loads in our columns. And if a column is relatively short and stout, it can crush, but that's not the typical failure mode. Typically, when a certain stress in the column is reached, the column buckles to the side. It bows out. And once that occurs, then you have a force times a distance, and a force times a distance is a moment. So then bending starts to occur and failure happens soon after. So basically, when we do column analysis, we need to try to figure out what is the stress going to be that is going to cause buckling to occur. So what is the critical buckling stress? And the first engineer or scientist to figure this out is Leonard Euler. He was among the first to come up with an equation to find how much stress or how much load. So we've got a load applied to our column, which when it's spread out over the area, the cross-sectional area of the column causes stress. How much stress causes a column to buckle? So he came up with Euler's buckling stress, or load, depending on whether or not you divide it by area. So what he found is that the load that will cause failure, and we'll give it a little E subscript for Euler, he found that that load, that critical load that is going to cause buckling to occur, is equal to pi squared times EI divided by L squared, where L is the unbraced length of the column, and E, we've talked about before, is the modulus of elasticity. And I, we have also talked about before when we talked about beams, is the moment of inertia. So the only thing here is that in a beam, we can control which axis the column bends about. But if we have a free-standing column, if it's not braced in any particular direction, it's going to bend about its weak axis. So this is going to be the least moment of inertia. So in other words, it's going to be the moment of inertia about the y-axis rather than the moment of inertia about the x-axis. And if we take this equation, this Euler equation for buckling load, and divide it by the area and do a little rearrangement, we come up with the Euler stress, F sub E. This is the Euler buckling stress right here, F sub E, and it is found by taking pi squared times E, times the modulus of elasticity of the material, divided by L over R squared. So that introduces a new variable, little r. What is the little r? R is the radius of gyration. And rather than giving a technical definition of what it is, I can best describe it in simple terms as it affects how stiff something is, how stout it is, how well it can resist vibration, or in this case, buckling out to the side. So, and again, isn't just like I. There's a radius of gyration about both the x and y axis, and we want to use the least radius of gyration, because a column, if it's allowed to buckle about either x or y axis, it will buckle about the y axis. The y axis for wide flange beams, at least when we're talking about wide flanges, the y-axis is the weak one, so that's the axis it's going to buckle about. So this is Euler's equation, and he had it very nearly right. It's been hundreds of years, and we've only really made one modification to Euler's formula, and that is has to do with effective length. So I'm going to change my pen color here and come back and add a variable k, capital K. So this is the equation we will use. We will use the coefficient k in the equation. So the Euler stress is pi squared times E over KL over R. Okay? And so what K does is K, if we are talking about a pinned column, which is most common, meaning that either end is free to rotate, and when it buckles, it will buckle in one curve, then the K value for this is 1.0. Theoretically, it's 1.0, and also the recommended value for design is also 1.0. So if we have a pinned column, K is just equal to 1, which essentially means it's almost as if it disappears. It doesn't really matter. 1 times the length. So so for a pinned column, it's 1. If we have a fixed column, so if we have a column that is like buried in concrete or is braced in some way to prevent rotation to occur, then when it buckles, it's going to be a compound curve, like a compound, what is it called? A recurve bow, I think. I don't know. I'm not really into archery, but I think that's called a recurve bow. That type of curve that curves out, and then it curves back the other way, and then it curves in the other direction again a third time. That is going to result in a shorter distance here, a shorter distance between these inflection points where the curve changes direction from curving to the right to curving to the left. And so that shortened height leads to a K value of, I'm just going to give you the recommended value for design. Theoretically, in theory, it should be 0.5, but for design purposes, we want to use a K value of 0.65 for when we have a fixed column. Okay, and then we could have a combination of a fixed space with a pinned connection on top. What is that going to look like? Well, it's going to kind of do this curve to the right, curve to the left, but then it'll just curve to the left and go back to the pin. So the inflection point is right there, and that's a little bit longer. Okay, so therefore we use a k value, a recommended design k value of 0.80. And then the last type, I'm going to actually draw my base a little higher up this time, is fixed free, like if we have a flagpole or telephone pole, or some sort of pole that's buried in the ground, it's not permitted to rotate, and the other end is just completely free. Well, if this buckles, it's going to curve out, and if we kind of continue that curve, that doesn't actually curve underground, but use our imaginations to complete the curve, that actually makes a very long distance between inflection points. And so for this, the k value is actually greater than 1. K, the recommended value for design purposes, in this case is 2.1. In theory, it should be 2.0, but for design purposes or analysis purposes, we want to use 2.1. Okay, so let's take a look at an example. Let's say, let's look at example 18.3 in the textbook. So for this example, we have a pinned top with a fixed base. So what does that tell us? Well, right away, we want to use a k value of 0.65. And it's made of a 3-inch diameter standard weight steel pipe. So 3-inch standard weight pipe. We're going to need to look that up in the appendix and find some properties of a 3-inch standard weight pipe. So I've looked it up in Appendix B. A 3-inch diameter standard weight steel pipe has an area of 2.07 square inches. It has a moment of inertia of 2.85 inches to the fourth, and because this is a pipe, it's round, it's the same in both the x and the y directions. If we were talking about a wide flange, it would have two distinctly different moments of inertia. And radius of gyration, same thing. There's only one radius of gyration given, and that is 0.791. No, I'm looking at the wrong row. That's for a 2-inch pipe. 1.17. That's 1.17 inches. The units for radius of gyration is just the inch. Okay. It's a steel pipe, so that means the modulus of elasticity is 30,000 KSI. And the length of our column here is 12 feet. And I just realized that when I looked up here at the different K values, I looked at the wrong diagram. We have this situation right here. And so that means our K value is actually 0.8. We have pinned fixed, not fixed fixed. So K value is 0.8. So I think we've got all of our variables. We're ready to plug into the equation and start solving, but I'm just about up against my 15-minute limit, so I'm going to pause the video here and we'll resume the calculation in the next video.